Gabby is a master's candidate at the University of Alberta studying the petrogenesis of the Hogem batholith using a combination of whole rock geochemistry and zircon, uranium, lead, lutetium, hafnium, oxygen isotope, and trace element geochemistry. Gabby is also a 2020 Geoscience BC scholarship recipient. Gabby, we're looking forward to hearing your presentation and getting questions from the audience, so I'll turn it over to you.
Thanks, Krista. Share my presentation here. Okay, so thank you for the nice presentation, Taylor, on Quesnel terrane. We're still in Quesnel terrane for my presentation. We've just moved north. So first, I'd like to thank my co-authors, everyone that's helped me collect this data, as well as the funding bodies for this research. My project specifically is in conjunction with the BCGS's Hogem batholith mapping project, so I'd like to thank them as well. Taylor already gave a background on Quesnel terrane, but the north is a little bit different. It is an accreted terrane with an interpreted oceanic arc affinity, just as a background. The terrain map on the right there of British Columbia shows the black box, and this shows the location of the Hogem batholith within the province. In the area of Hogem, this has variable Paleozoic basement, and along the strike of Quesnel terrane, as we've seen, there's many Mesozoic plutons, and these are important hosts to porphyry mineralization within the province. This includes Hogem batholith, and there are copper gold deposits in the area, including Lorraine and Quinica. So moving on to a bit of background on Hogem geology now. The Hogem batholith was emplaced into the Triassic Nicola group, volcanic and sedimentary strata. On the map to the right, this is shown by the green unit. The basement is the Paleozoic lay range assemblage, and this is exposed to the east, but not shown on the map. And the Pinchy-Injanika dextral strike slip fault system cuts the batholith to the west and juxtaposes the Cache Creek and Stikine terranes against it. Focusing in on Hogem here, the batholith is comprised of 4 main intrusive suites, the oldest being Thin Creek Suite, shown by purple. Next is Ducklin Creek Suite, shown by oranges, and 10 kilometers to the southeast of our mapping area is the Lorraine deposit. The middle area here is Osilinka Suite, and the youngest intrusive suite is called Mesolinka and is shown in the northwest by these pinks and browns. So for my research, I've conducted zircon uranium lead geochronology using laser ablation. A summary of these results are on the right on this timeline. Each symbol here represents a single sample that has been dated in each intrusive suite, and these correspond to the black triangles on the map to the left. Starting with the oldest suite and working our way up to the younger suites, this is Thin Creek Suite. Thin Creek, we've dated at 207 to 194 million years old and consists of mainly diorites and granodiorites that commingled with older hornblendite and gabbros. Next is Ducklin Creek Suite. Ducklin Creek Suite is dated at 182 to 175 million years old and consists of mainly alkalic cyanites that intruded older biotite clinoperoxenite. Next is Osilinka Suite. Osilinka Suite is full of inherited zircon, so the youngest inherited zircon age in the sample is dated at about 160 million years old, which is used as the best estimate of the crystallization age. And these consist of weakly paraluminous leucocratic granites. And finally, Mesolinka Suite. Mesolinka Suite is dated at 135 to 128 million years old and consists of tonalite as well as weakly paraluminous equigranular and K-feldspar porphyritic granites. The next portion of my research is on zircon lutetium hafnium isotopes, and these were also collected using laser ablation on the same zircons that were dated for uranium lead. The figure on the right shows those single zircon crystallization ages on the x-axis, with the corresponding zircon epsilon hafnium on the y-axis. The light gray bar shows the entire range of normal mid-ocean ridge basalt epsilon hafnium values. And as you can see, the Hogem data all fits within this. So the results are all relatively juvenile. Thin Creek shown in purple, Ducklin Creek in orange, and Osilinka Suite in red all have relatively similar mean epsilon hafnium values, with Thane Creek being the most juvenile, whereas Mesolinka Suite is a bit more variable. The tonalite has a mean value of 8.8, whereas the equigranular granite shown by diamonds is more intermediate with a mean of 7.5. And the K-feldspar porphyritic granite is the least radiogenic sample with a mean epsilon hafnium of 6. We also conducted zircon oxygen isotope analysis using secondary ion mass spectrometry. Again, these were collected on the same zircons as analyzed for uranium, lead, and hafnium. And oxygen isotopes are useful because they may be used to assess the relative amount of crustal recycling within a sample or within a magma. And this is because the mantle does not significantly fractionate oxygen. So the figure on the right, we've now flipped the zircon epsilon hafnium to the x-axis and have the corresponding zircon delta 18O value on the y-axis. The yellow bar represents the mantle range of oxygen isotope values, and values greater than this indicate magmas that have some source that has interacted with the low temperature hydrosphere or crustal recycling. So Thane Creek, Ducklin Creek, and Osilinka Suite, as well as those Mesolinka tonalites, are all mostly mantle-like or just slightly higher than mantle values. Whereas the Mesolinka granites indicate they have some sort of hydrosphere interaction in their source because they're higher than mantle values. And we also looked at zircon trace elements. Shown here are the zircon rare earth element concentrations normalized to chondrite for each intrusive suite. For the purpose of this talk, I'm going to focus on Europium anomalies, and Taylor had a good introduction with that because they may be used for proxies for oxidation state or water content in magmas. Less negative or more positive Europium anomalies apparently indicate either increased oxidation or water content in the magma. And this is because elevated water content may cause suppression of feldspar crystallization to later in the magma, and which would result in a higher uranium or Europium anomaly in the zircon. Whereas an oxidized magma may convert Europium 2+ into Europium 3+, which cannot be incorporated into plagioclase, but can be incorporated into zircon. So looking at Thane Creek Suite here, we're looking at the hornblendite shown by the circles versus some diorites. So as you can see, the hornblendite has a flatter Europium anomaly. This may solely just be due to plagioclase accumulation in the diorites versus less plagioclase in the hornblendite. Whereas in Ducklin Creek Suite, we're comparing two cyanites with similar mineralogies. The older cyanite, dated at 179 million years old, shown by the circles, has no Europium anomaly, whereas the square cyanite is younger and has a more negative Europium anomaly, indicating a changing oxidation state or water content possibly through time. Osilinka Suite are inherited zircons. So these are just reflecting the source of their zircons, not the actual magma itself. And Mesolinka Suite, we are comparing two granites. The older granite, again, has a less negative Europium anomaly with a Europium anomaly of 0.6. And the equigranular granite, which is slightly younger, has a Europium anomaly of 0.3. Again, so there's a changing oxidation state or water content through time. We also did some zircon titanium thermometry. Again, we have the single zircon crystallization age on the x-axis here, and on the y-axis we have the titanium and zircon temperature. And this just shows there is a change in temperature through time, and it's not linear. Most interesting are Thane Creek and Ducklin Creek Suite, which both have relatively lower temperature samples and relatively higher temperature samples, and both these correlate to higher Europium anomalies and lower Europium anomalies, indicating possibly a higher oxidation state or water content at lower temperatures, which would be more favorable for porphyry formation. So what are the implications of all this? Pre-170 MA, we are crystallizing Thing Creek and Ducklin Creek suites, which have the most juvenile epsilon hafnium and most mantle-like zircon delta 18O values. They also have a variation in titanium temperature through time, indicating various magma inputs. And this all indicates the transition from an island arc setting into a syn collisional setting in Quesnel terrain. Post 170 MA is Osilinka Suite. These are inherited zircons, which predominantly overlap with Thing Creek and Ducklin Creek Suite results, indicating syn to post accretion in north central Quesnel terrain at the time, which caused remelting of Thing Creek and Ducklin Creek Suite. And finally, Mesolinka Suite, post 140 MA. We have the mantle-like tonalite with more of a hydrosphere and less radiogenic hafnium in the granites, indicating a mix of sources. There's evidence of crustal recycling due to post-accretionary crustal thickening, as well as new juvenile magnetism. So in conclusion, zircons from the composite Hogem Batholith record changing tectonic environments in the 4 intrusive suites. This study has provided an opportunity to study the background magmatic conditions of a potentially porphyry-forming environment, and varying tectonic setting through time likely had an impact on the magmatic fertility in the Hogem Batholith. Thank you.